In this video, we're going to learn about solubility, and one of the key skills you're going to have after you watch this video is being able to predict whether something is going to be soluble in water or another solvent, just by looking at it and knowing something about the structure. Solubility depends on the relative strength of solute-solvent interactions compared to solute-solute or solvent-solvent. So here, this is if you have sodium chloride dissolving in water. So you have the interaction of the water molecules to each other and the sodium and chloride to each other. But then the water has to come in and compete with that. It turns out that like dissolves like. So ionic and polar solutes will be soluble in polar solvents, such as water, and nonpolar solutes will be soluble in nonpolar solvents. So you're going to have to use what we learned about drawing Lewis structures, using VSEPR theory, valence shell electron pair repulsion theory, to determine the polarity of the bonds and whether or not the overall molecule is polar. And then you'll be able to figure out what kind of solvent it will dissolve in. So similar forces mix to form solutions. And remember, solution is just another word for homogeneous mixtures. So here are some images of some different solutions. These are copper 2 acetate solutions. And what type of compound is copper 2 acetate? So we have a metal, a transition metal, and a polyatomic anion. So this is an ionic compound. This is an ionic compound that's soluble in water. So we have ion dipole for the ions interacting with water, and then hydrogen bonding for the water itself. So like dissolves like. So I want you to take a second and pause this video and see if you can figure out which substances are likely to be soluble in water. All right, let's take a look at ethanol. So hopefully you looked at this compound and saw that if you have OH, what's your intermolecular force going to be here? Hydrogen bonding. So it's polar. So would it be soluble in water, which also has hydrogen bonding and is polar? Yes. All right, then we have carbon tetrachloride. So here you have your Lewis structure. And even though each of these bonds has that electronegativity difference, so you have polar bonds, but overall it's nonpolar. So will it be soluble in water? No, it won't be because it's nonpolar and water is polar. All right, how about potassium chloride? What type of compound is potassium chloride? You have a metal and a nonmetal. This is an ionic compound. A soluble ionic compound, which you know from your solubility rules. So it will dissolve in water and you'll get that ion dipole interaction. Hydrofluoric acid. If you draw a Lewis structure, it's just H with a single bond to F. F is much more electronegative than hydrogen, so you have an overall dipole moment going this way. So it is polar. So yes, it should dissolve in water, it should be soluble in water. And if we look at heptane, which is a 7-carbon chain with hydrogens all around it, and hopefully you know by now that any of these carbon chains with just carbon and hydrogen are non-polar. So if it's non-polar, it is not going to be soluble in water. All right, so just practice a bunch of substances like this. Get familiar with, you just figure out if it's polar. If it's polar, then yes, it should be soluble in water. If it's non-polar, it won't be. So this polarity thing kind of tells us how soap works. So far we just talked about things that have one intermolecular force. But I did mention that you can have big compounds that have more than one intermolecular force present. So soaps and detergents have a hydrophobic end, which interacts with grease, and a hydrophilic end, which allows a micelle to dissolve in water and be washed away. So hydrophobic means water-fearing, and hydrophilic means water-loving. So there's a polar end, which is hydrophilic, means it loves water, it dissolves in water. And then you have this non-polar chain here, which will stick to the fats or the grease on your hands or your clothing. Then you can see this guy, there's a whole bunch of them that go around like this. So you have this oil particle surrounded by all these non-polar tails. And then the polar tails kind of go out like this and form this micelle, which is an aggregate of molecules in a colloidal solution, such as those formed by detergents. So this entire thing makes up your micelle. And then the bulk water around here can wash it down the drain, either off of your hands or off of your clothes in the washing machine. So soaps and detergents actually use this combination of a non-polar end, which is using just those dispersion forces to attract each other, and then a polar end where you actually it's interacting with the dipole moment of water. So it's soluble in water and can wash away. So here are some different intermolecular force combos. So this is ethanol. It has this OH bond over here, so it's going to have hydrogen bonding and a dipole, and then a non-polar end, but it's quite small here. So this is miscible, it will dissolve in water. As you increase the carbon chain, you still have the hydrogen bonding over here in this dipole moment, but you're really increasing the non-polar end. So then it's a little less soluble in water. If you make that carbon chain really long, even though it has this OH, there's a competition between these two, so it's not very soluble. Solubility is going to decrease as relative energy of hydrogen bonding decreases and dispersion increases. So at this point, those forces you're gonna have to take the entire molecule into account and see what's the primary force present, the primary intermolecular force. Dissimilar forces do not mix, and these form heterogeneous mixtures. So for example, this image here shows water at the bottom and pentane on the top. And you can see that they're not mixing. The pentane is staying floating on the top. Part B, this is oil and vinegar in salad dressing. And I'm sure you've all seen how they separate into layers. This is an oil spill from a tanker, which demonstrates that petroleum and seawater are not miscible, which is why when you have an oil spill, it will spread out over the surface, but it spreads in this really thin layer, so it can actually spread really far on the ocean. But it is kind of good that it'll stay on the top rather than sink to the bottom, so that then we can go in and try to mitigate the problem. So that finishes up everything we were going to talk about in chapter 10. We talked about intermolecular forces, dispersion forces, dipole-dipole, hydrogen bonding, and ion dipole. We looked at phase diagrams and polarity and solubility. So go ahead and practice all those concepts until you have mastered them.